Okay, so in chapter 4, we're looking at anti-differentiation. So if we look at the antiderivative, it's a symbol that looks like this, but let's kind of remember what, trying to get my screen bigger for me. Anyway, I think I can just, there we go. So it looks like this. It's kind of like a long elongated X or S, but anyway, so that's not very good. Looks like that. That's a pretty good one. Anyway, we're looking at anti-differentiation is undoing differentiation. And differentiation is taking a derivative, right? So taking an antiderivative or taking an integral is another way that this is talked about. So if you hear me say the word integral, taking an integral is taking an antiderivative. All right. So let's just remember a couple things so you can answer these in your head real quick. But the derivative of x squared with respect to x, what's that? That's going to be 2x, right? And the derivative, and I could do it different ways, but I'll just write it as d dx. Derivative of x cubed is 3x squared. So I think I use these in the videos, but basically, if we want to undo this, we can, if I want to undo this and do an anti-differentiation and I do an antiderivative of 2x, and then with respect to x, we put the dx there. And so really this is what we're taking the antiderivative of with respect to x. You can answer this question by saying, hey, the derivative of what is 2x? Well, the derivative of x squared is 2x. So the antiderivative of 2x is going to equal x squared would be one option because if you take the derivative of x squared, you get 2x. But if I had the derivative of, if I took the derivative of x squared plus any constant, so let's just say it's 2, this would also be an antiderivative because the derivative of x squared plus 2 is also 2x. So really we can, if I had a negative number in there, x squared minus 2, and I took that derivative, I'm still getting 2x. So really I can add any constant, positive or negative, to this. And so instead of writing it as just x squared, whoops, what I can do is put plus c. Okay, so the antiderivative of 2x with respect to x is x squared plus c. And then, of course, the same thing here. If the derivative of x cubed is 3x squared, then what is the antiderivative of 3x squared with respect to x? And so this is what I'm taking the antiderivative of. Of course, we already know the answer. The derivative of x cubed is 3x squared, so that would work, but I could also add any constant c. So if you're pretty good at derivatives, which we are, I know some of the word problems on the test kind of trip some people up. So we'll go through that, make sure you understand that. I'm going to give 10 points back since you had to take that without any note cards or anything like that. So anyway, we'll get squared away on the test on any stumpers because everybody probably had at least one or two of them. If you didn't, congrats. So anyway, but hopefully this makes sense. So let me clear this. So I got to remember how to do that. Whoops. Oh, there we go. Clear everything. So I'm trying to do it where I don't have to erase it all. Okay, so basically if I'm taking the antiderivative of x to the fifth with respect to x now, so you can try and answer this, hey, the derivative of what is x to the fifth? Well, kind of x to the sixth, right? Because the derivative of this would be, if I go down here, the derivative of x to the sixth, we know is 6x to the fifth. Well, I don't have 6x to the fifth, so I have this 6 that I need to take into consideration. So I'm going to need to divide that by 6. So it's going to be x to the 6th divided by 6. So the derivative of this, 6x to the fifth, but then the 6's would cancel, and I'm just left with x to the fifth. Anyway, plus c. So we're starting to get a pattern here And the pattern is this. So we have a theorem for antiderivatives, the power rule. If I have the antiderivative of x to the nth power with respect to x, then that's going to be the derivative, basically, once again, the derivative of what is x to the nth. Well, I can add 1 to the power on top, but then I got to divide by that power. And then, of course, there's a family of antiderivatives, which I talked about up and down shifts in my videos. So anyway, I got to put a plus c there. So when I take the derivative of the right side, I'm going to end up with x to the nth power. As long as this is true if n is not equal to what? -1. Because if it's equal to -1, then I have x to the 0 divided by 0, which is undefined. So we have another theorem, and this theorem is when n equals -1. If n equals -1, what do I have? I've got the antiderivative of x to the -1 power with respect to x, but we can rewrite that as the antiderivative of 1 over x with respect to x, 1 over x dx. And this is going to be the natural log of the absolute value of x and then plus c. So anyway, natural logs, if you learned about logs, we talked about them briefly earlier this term, but if I've got log base 2 of 8 is what? Well, if I say, if I call that x, then 2 to the x power equals 8, but 8 equals 2 to the third power, so x would equal 3, right? So log base 2 of 8 is 3. Natural log is just log base e. So if I have log base e of, let's just call it e squared, what would that be? E to what power is e squared? Well, that would be 2. All right, so anyway, that would be an easy example of that. But anyway, natural log. So natural log has some applications here. This is one of them. So this is just a one-off thing for the power rule. If you get 1 over x and you try and do the power rule and get x to the 0 over 0, that doesn't work out. So it's natural log of the absolute value of x plus c. And I give some more details, I believe, in videos on that as well. All right. So anyway, so we have some nice theorems. So let's look at some examples here, and let's use our theorems here. So example, if I have the antiderivative of cubed root of x with respect to x, let's just do this one. Well, the cubed root of x, we could rewrite that as a power. That'd be x to the 1/3 power with respect to x. So that's going to be the trick here. And then what I do is the power rule. So the antiderivative, I'm going to add 1. So I'm going to write this out this time, but normally I won't. And then divided by that. So 1/3 plus 1 divided by 1/3 plus 1, and then plus c. But of course, 1 is 3/3, right? So that ends up being 4/3. So this is going to be x to the 4/3 divided by 4/3 plus c. And of course, that's not a good math way to write your answer. So when you divide by 4/3, that's going to be the same as multiplying by 3/4. So this is going to be 3/4 x to the 4/3. And I'm just going to write it like this first, and then plus c. And of course, what did we have? We had a root first. So what the book might do, the denominator is the root and the numerator is the exponent. So they might write x to the 4/3 as the cubed root of x to the 4th. And of course, the cubed root of x to the 4th is like x cubed times x. So it's the cubed root of x cubed times the cubed root of x. And of course, this is just x. So it's be 3/4. What you might see is 3/4 x cubed root of x and then plus c. So they might write it like that, but ultimately, you know, it's 3/4 x to the 4/3 plus c. So if you, by the way, what's really nice about this section is we can check our answer. And how do we check our answer? We can just take the derivative of our answer. So if I take the derivative with respect to x of whatever antiderivative I got, what do? I take that, I drop it down in front, and 4/3 times 3/4 cancels out to 1. And then it's going to be x to the 4/3 minus 1. So when we take a derivative, the power rule for a derivative, we subtract 1 from the exponent or subtract 3/3. That's x to the 1/3 power. And of course, the derivative of a constant is 0. So anyway, it's x to the 1/3, which is what I had in here. So it is kind of nice now that we've had derivatives. When we're learning antiderivatives, we can definitely verify our answers. So let's look at a couple others quick here. So if I have the antiderivative and a couple other theorems, stayed with red. If I have the antiderivative of some constant times a function, a constant times f of x, then what I can do is I can pull that constant out front, and that would be the same as the constant times the antiderivative of the function. And so let's look at a quick example of this. If I have the antiderivative of 3x to the 7th power with respect to x, what I could do is I could take that 3 out in front by my theorem, so I can pull a constant out in front by multiplication. It's going to be the antiderivative of x to the 7th. Sorry, that's not a very good s. X to the 7th with respect to x. And then what I can do is that's going to be 3 times whatever that antiderivative is, and what it ends up being is x to the 8th divided by 8. And then we could put plus c, like if you wanted to have parentheses around this and then put plus a constant and have, we could do plus c1 and then multiply the 3 through, but 3 times a constant is a constant. So really what I'm going to do is I'm just going to say it's 3 times x to the 8th divided by 8, and then just put the plus c at the end. Just make sure you don't forget that plus c, because that's definitely worth a point every time. Or easier way to write this, 3/8 x to the 8th plus c. And then if I want to check that, all I got to do is take the derivative of my answer for a check. And so 8 would cancel with this 8, and I'm left with 3x to the 7th, and then derivative constant is 0. And that's what I had inside there. So the derivative of or antiderivative of a constant times a function is a constant times the antiderivative of the function. That matches our derivative theorem that a derivative of a constant times a function is the constant times the derivative of the function. All right. Now we have a couple other theorems. The antiderivative of f plus g evaluated at x with respect to x is going to be the antiderivative of f of x with respect to x plus the antiderivative of g of x with respect to x. Now this is also going to be true if it's a minus sign. So the antiderivative of the sum is the sum of the antiderivatives, and the antiderivative of the difference is the difference of the antiderivatives. So some of these have similar rules to what we had. So let's just look at an example of this. If I've got the antiderivative of the square root of x plus x to the 4th with respect to x, this is going to equal the antiderivative of, I'm going to write it as a power, x to the 1/2 dx plus the antiderivative of x to the 4th dx. So once again, using the power rule, this is x to the add 1 to 1/2. We get 3/2 divided by 3/2. And then I could say plus a constant, plus c1 here, and I could say plus c2 here, but adding 2 constants is still a constant. So what I'm going to do is I'm just going to put the constant at the end. So plus c, and then of course this 3/2 we're going to write as 2/3. And then if you want to use math etiquette, it's going to be 2/3 square root of x cubed, rewriting that power, plus x to the 5th over 5, or 1/5 x to the 5th, I don't care how you write it, plus c. And of course the book might rewrite this one as x times the square root of x, because you could write that as x squared times x. Wait a minute, the square root of x squared is actually the absolute value of x. So they might say 2/3 absolute value of x times square root of x. But anyway, this is works as well. Okay, and this is the the fractional exponent version of the answer, and they are equivalent. So I'm not going to beat you up too much on that stuff. I'm just telling you what math etiquette is. All right. So what if I have something like this? The antiderivative of x cubed times 2x squared plus 3 with respect to x. The question is, can we handle this in section 4.1? And the answer is we can handle it if we try and make this look like it forms that we can handle. So if I multiply this through, I could certainly do that. Then I'm going to have the antiderivative of 2x to the 5th with respect to x plus 3x cubed. And so then integral of the sum is the sum of the integral. So I'll split that next. So if I multiply using the distributive law there, then I can say the integral of the sum is the sum of the integrals. And so I'm just going to write this out in detail this time. And if I do this, integral of 3x cubed dx, and then what can I do with these constants? I can pull those out in front as well, right? So this is going to be 2 antiderivative of x to the 5th with respect to x plus 3 antiderivative of x cubed with respect to x. Now I can go ahead and take the antiderivative. So it's 2 times, and this is going to be x to the 6th over 6 plus 3 times, and this is going to be x to the 4th over 4. And then don't forget the plus c. And then, of course, this 2 and this 6 would cancel and just have a 3 on the bottom. Okay? So anyway, so it'd be x to the 6th over 3 plus 3/4 times x to the 4th plus c. And then, of course, we could take the derivative of this back and make sure that it matches our hopefully correctly multiplied out version of that. So there's some methods in 4.2 that can make life a little easier, because if this was, trinomial times a trinomial, that's a lot of multiplying out and stuff like that. So there's some substitution methods that we're going to do as well. All right, so I'm going to take a quick breath break. But if I'm going to let you out early, I want to go through a few things. Any questions specifically so far? Okay, take that as a no. And then a couple of other things. If we know that the derivative with respect to theta, derivative of tangent is secant squared, right? So similarly, if I have the antiderivative of the right side, the antiderivative of secant squared theta with respect to, with respect to theta, my screen just jumps and gets big on me every once in a while. If I want this, then basically I can say, hey, the derivative of what is secant squared? Well, the derivative of tangent is secant squared. So this would be tangent theta, but what do I got to add? I got to add a c plus c there, right? Because if I take the derivative of the right side, the derivative of constant is 0 also. So tangent theta plus 5 would also be an antiderivative. So we have a family of antiderivatives. That's why we put the plus c. So unless you're given more specific information, that's what we're going to go with. So we have all those trig antiderivatives going the other way. So if I have the antiderivative of cosecant cotangent, well, the derivative of what is cosecant cotangent? The derivative of cosecant is minus cosecant cotangent. So cosecant gets us close, but since this doesn't have a minus on this side, I got to put it on this side, because the derivative of cosecant minus cosecant cotangent, and then the opposite of that would be a plus cosecant cotangent. Whoops, forgot my d theta. Anyway, and I got to have my plus c on the right. So we have all those trig antiderivatives as well for the derivatives that we know. Okay. And so that hopefully is enough to get you kind of through 4.1 and stuff. I know there was some graphical ones. I'm going to let you watch the videos for that and just try and hammer out some easy peasy examples for this and in 4.2. So in 4.2, we have a couple of like a substitution method. So we've got some more involved functions or things that we're taking the antiderivative of. And so we're going to use substitution. So we're going to sub. Okay, making me hungry. Need a Subway sandwich. So anyway, if I have something, I'm going to do something. Let's do this. If I've got the antiderivative of x squared over x cubed plus 3 to the fourth power with respect to x. All of a sudden, this can get very challenging trying to use some of the simple rules that we had before. So what I want to do is I want to rewrite this. And if I can use substitution, this is a function to the fourth power. So it might be easier if that was like a u to the fourth power or something like that. So that's what we do a lot. We're going to let u equal x cubed plus 3. And then what's the derivative of u with respect to x? The derivative of u with respect to x is 3x squared, isn't it? And notice that I have an x squared here, and I have an x squared here, and then I also have a dx up here. So what I can do, and I'll do this every time, is I'll just attach that dx to the right. So when I write u equals x cubed plus 3, I'm just going to put du on the left, and I'm going to attach the dx on the right. And then what I can do is I can say, hey, I can get rid of that 3 and put it on the other side. So du divided by 3 equals x squared dx. And so what I'm going to do then is this u, I'm going to plug in right there, and I'm going to rewrite this. So what is this equivalent to? This is going to be equivalent to the antiderivative of what? Well, du over 3, remember 1/3 I can pull out in front because the antiderivative of a constant times a function. So I can pull that 1/3 out that I've got right here. And then the x squared dx, I'm replacing with what? Du over 3, right? So I've got the du over 3. So I've got that. And then what about the bottom? So then that just leaves a 1 on top. And then on the bottom, I've got u to the fourth power. So now, all of a sudden, is this antiderivative here much easier to handle? Taking the antiderivative of 1 over u to the fourth? Yep, because I can say that's going to be 1/3 antiderivative of u to the minus fourth du, and then I can use my power rule. So this is going to equal 1/3 u to the add 1. So if I add 1, -4 plus 1 is -3, divided by -3, and then plus c. So this ends up equaling -1/9 u to the -3rd. So I'm going to drop that down and make it positive. -1 over 9u cubed plus c for the antiderivative. And then, of course, what I want to do is I want to sub back in what this u is. So I'm going to put that x cubed in there. So my final answer, I'm going to erase, give myself a little room here. It's not as easy to erase on this, but anyway, so when I do that, then this is going to be equivalent to, if I back substitute for that u, it's going to be -1 over 9 x cubed plus 3 to the third power, and then plus c. So this is the antiderivative of that. So this is using a method called substitution to rewrite the problem. So usually if I have something in parentheses, maybe let u equal that. So I've got the book has some nice examples. I got some nice examples on your videos and stuff like that too. So this would be an example in the section 4.2 substitution. Here's, I'm going to do one more of these. But anyway, once again, how do I check the answer? I can check this by taking the derivative with respect to x of my answer and make sure that I end up with this. And of course, I would rewrite this as minus 1/9 x cubed plus 3 to the minus 3 power, and then use the power rule. So minus 3 times minus 1/9 is minus 1/3. And then this thing to the second times the derivative of what's inside. Derivative of what's inside is 3x squared. So I've got the x squared. Those 3's would cancel. And the minus sign canceled, so that ended up being positive. And it ends up being this here. And of course, the derivative of a constant is 0. You can always check by taking the derivative of your answer, which is really nice, especially for even ones that don't have answers in the back of the book. So I'm going to do one more example. I'm going to do a trig example, hopefully. And let's just look. The antiderivative of tangent x secant squared x dx. Now, what some of you might do is say, hey, tangent's 1 over, or sine over cosine, secant's 1 over cosine. So I could rewrite that as sine over cosine cubed. I could use substitution that way, but you could actually use substitution right away. So secant squared, anyway, if I let u be something, the derivative, well, do I want u to be secant? Then I'd have u squared, but the derivative of secant is secant tangent. There's actually 2 different ways we can do this. But the easier way that I see right away is if I let u equal tangent x, then du equals secant squared x dx. And so what I can do is, where this is, I can plug in a du. So that can go there, and then I can plug a u in for the tangent x. So this would be equivalent to the antiderivative of u du, right? Because I plug in du there. And this is pretty easy. I can just use the power rule because that's u to the first. So this is u squared over 2 plus c. Don't forget the plus c. And then back substitute. So when we back substitute, just put back in what u was. U was tangent x. So this would be tangent x quantity squared, or the way we write that, tangent squared x over 2 plus c. And if I take the derivative of that, that actually ends up being tangent x secant squared x. So this is one way to do substitution on this. There's actually like 3 different ways that work. There are some substitution ways that don't work. So if you're trying substitution and it doesn't work, try a different style of substitution. So let's just look at this one more time. So I got tangent x, and then the secant x, secant squared x, I'm going to write that as secant x quantity squared. And then what I might think in my head is, hey, I want, this is in parentheses, so what if I let u equal secant x? Then what's du equal? Derivative of secant is secant tangent. So it's secant x tangent x, and then what did we do in this section? We're writing the dx on the right side. So instead of du dx on the left, I just put the dx on the right. And then what do you notice? I've got 2 of these. So this is like tangent x, and then secant squared is secant x times secant x, right? And then dx is what I got. But I have tangent x secant x dx. I could replace all of that with du. So this is equivalent to du for that part. And then the u could go right in there for the secant. And I end up with the same thing, integral of u du, which is, or antiderivative of u du, which is u squared over 2 plus c, same as what I had before. But in this case, what's u? U is secant x. So if I back substitute that in here, then this ends up being secant squared x over 2 plus c. So if you notice with trig, there's some different identities that end up working out, but this is a different looking answer that is also correct. So just if you got trig ones and the book's a little bit different, just make sure that, you know, that your work was correct and stuff like that too. But this is an example where the same problem could have a couple of different answers. And then the last version, I could let you try this on your own if you want. But I could write tangent as sine over cosine. and I could write secant x as 1 over cosine, so it's times 1 over cosine squared. And so this would be sine x over cosine cubed. And if I had this with respect to x, I would probably let u equal cosine x, so that'd become a u cubed on the bottom. And the derivative of cosine is minus the sine, and I could sub it in up here for that one, and then I'd have to attach a minus. So I'll let you work on that. So I'm out of time. I'm going to stop the recording and then see if there's any questions and go from there. I'll see you Wednesday.